I know.
Today we're going to take a look at section 9.2, which is called Multistage Experiments. I'm going to start with looking at a way of doing a diagram. You may have used these in the past, and you may not have. Almost all the diagrams that we do, or all of the work that we're going to do in this section, is going to involve one of these diagrams, and it's called a tree diagram. A tree diagram is a sample space model where each outcome is designated by a separate branch. And this is another one of those places where I'm going to define a whole bunch of stuff before I actually show you what this looks like. But the idea is that there are different outcomes possible, and we draw sort of a node or a dot with branches coming out of it. It may be two, or it may be more than two. And then there are potentially another set of branches coming out of this, again, maybe two or more than two. And they don't have to be the same number in each case, from branch to branch off of each node. None of that has to match up, although it often will. One-stage experiments are experiments that are over after one step, that is, one set of branches. So like when we rolled our dice and we got the 1 through 6, a tree diagram for that might look like this. It's a node with 6 outcomes. And we would write the outcomes value on each node, 1, 2, 3, 4, 5, 6. And I don't have space on mine. You can barely see my numbers, but we would actually write the probabilities along the branches as well. 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, because they're all equal in that case. Okay? A two-stage experiment, which is where we'll do most of our work, is experiments that are over after 2 steps. Ours will usually be 2 or 3. There's a couple places where you might have sets of 4, but usually 2 or 3. And you'll have 2 sets of branches. So the picture that I drew up here would be an example of a two-stage experiment. The first stage is the first set of branches coming off the first node, and the second stage is the second set of branches coming off the second nodes, both of them. Okay, so all of that would be my second branch. So if I did the same experiment with my dice that I rolled, and I rolled it 6 times, not rolled it 6 times, but I had 6 options, then if I had another, sort of roll after that, I could draw. It'd be really mean for me to have you draw this, but 6 branches off of each one of those 6 branches, right? I mean, that's what it would look like for that particular one. A nicer one might be doing a coin, because it only has 2 outcomes. So if you were to do a coin, I think we'll do a coin later anyway, but let me just show you how simple that one can look. You either toss heads or tails. And then after you do that, you do it again, you either toss heads or tails. So it has this beautiful symmetric imagery. Not all of them do, but that one would. Each of them are all a 1/2 probability, so all of our branches would have 1/2s along them. And that would be a completed tree diagram. Now, it's kind of like when we do any kind of diagram, whether it's draw a picture to solve an algebra problem, or whether it's doing Venn diagrams or truth tables or different things you've done in other courses. The diagram supports the work that follows. It doesn't actually give you the answer, but it allows you to find the answer. So a couple things that are really important is this next theorem, and it tells you how to use the tree diagrams to find the solution to a question. For all multi-stage experiments, the probability of an outcome along any branch of the tree is equal to the product of the probabilities along the path. And do whatever you need to box, circle, highlight this paragraph, because it's really important. Expect to see tree diagrams or something equivalent. And I'll show you an example in the notes today of an equivalent thing to a tree diagram that would be acceptable in a specific case. Okay? Expect to see tree diagrams. So if I go back up to this diagram up here and I wanted to know what's the probability of getting 2 heads, well, I would simply look at the branch that has 2 heads in it, and I'd multiply the probabilities along that branch. So I'd have 1/2 times 1/2. It would be 1/4. My answer would be 1/4. It's a 1/4 probability of getting 2 heads. Now, if it wants to know the probability of getting matching sets, like it says probability of heads, both heads or both tails, then I would do the same thing. I'd multiply along this branch, and of course it gives me the same 1/4. Don't mean plus, times, it's multiplication. But then what I would do is I would add these together. There are two outcomes that both answer my question, and I would add the individual answers at the end together. And you'll see us doing some examples of those. Now, back in 9.1, we used this phrase, mutually exclusive, and I talked about the fact that mutually exclusive are events that are happening within the same sample space, right? This one is the one that people get confused with it. It's the phrase independent events. These are events in which the occurrence of one event has no influence or outcome of the occurrence of the second event. So these are things where when I repeat it, the first outcome doesn't affect the second, right? If you roll the die the first time, whatever you get has absolutely no bearing on what you get the second time. When you have a baby, whatever you have first has no bearing on the baby you have second. So we have lots of examples of independent events, but there are events that are not independent. Whether it's sun shining out today has some influence over whether it's sun shining out tomorrow. It doesn't guarantee it, right? But it does change things. The fact is that it's sun shining today probably means that it's not going to be freezing and snowing tomorrow, but we do live in Oklahoma, so there's always a chance. But there's an effect, right? There is a correlation. There is something that says that they're not completely separated. Now, whether it's sun shining on January 1st and whether it's snowing on February 1st, that's probably independent events there because they're far apart. But that would be an example, okay? So this is and there's one more. It talks about what happens when you do have independent events. So if you have independent events E1 and E2, then the probability of them both happening, right? So this is an example of my tree diagram here. The probability of getting a heads and then another heads is equal, excuse me, to the probability of each of those events multiplied together. Okay? So the probability to get heads and heads is the probability of getting heads times the probability of getting heads. Because that's actually an independent event. There's no bearing on the second outcome depending on what the first one was. Now, the first example I'm going to do are not independent events, and you'll see why very quickly. So we have an executive committee of 10 members, 4 women, 6 men, and 3 are selected at random to attend a meeting in Hawaii. Sign me up, right? And then there's some questions. So let's go to the next page in questions. You don't necessarily have to, but it will help us to determine how we draw our diagram. It's going to ask us questions about the selection of the people based on gender. What's the probability that all 3 are women? What's the probability that at least one's a man? Okay? So the only thing that matters in my diagram is not the individual people, but the gender of the people. That's really important because it simplifies the diagram. I don't need to call them, like A is female, B is female, C is female, and I don't need to do 10 nodes. I only need 2. Because the only thing I'm really comparing is the genders in the situation, not the individual people. Does everybody make sense of that? Okay? So we draw this diagram where I have, I'll do M and W for man and woman. You could do male and female if you want or something else, but this will work. Boy and girl, B and G would be okay. I think we can come up with lots of options, but. Okay, so when we start out, there's a hat with names in it. And there are 10 names in it. So each of my probabilities happens of drawing 10 names. Okay? Out of 10 names, from among 10 names. So what's the probability that I reach in and I draw out the name of a man? 6. How come? There's 6 men. What's the probability that I draw out the name of a woman then? 4. Now, along each branch, what you should notice is they always add up to the number 1. That has to happen, okay? So this is the number 1. But I'm not having just one person go to Hawaii. I'm going to have 3 people go to Hawaii. So I need to repeat this diagram a second time for a second person. Again, I will either get a man or a woman. But whatever I chose first, I'm not putting their name back in the hat. They're not going to Hawaii twice, right? We don't take the number out or the name out and then put it back in. We take the name out and we leave it out. So how many names are currently in my basket now? 9. Because we only picked 1, yeah. We considered what the one could have been, but we only picked 1. So no matter what's left, this looks like I'm writing repeating decimals. I'm not. I'm writing the bottoms of fractions. There's only 9 that are still in the basket. Not only that, but it matters whether I picked a man first or a woman first because it's going to affect the probabilities after that. So we have to go along the branches carefully. So if I'm going along the very topmost branch, I've already picked one man out of the basket. How many men's names are still left in? 5. How many women's names are left in? The same 4 from before because I didn't select a woman. Okay? Each of these outcomes are different outcomes. It's like when you watch the last Avengers movie and you see all the different continuums going. Y'all know what I'm talking about, right? And this one piece affected what happened next. This is what we got going here. It's right here, Avengers, in my lesson. It's the first time I've said that on an iPad. So there you go. All right. Bottom branch. We picked a woman. Right? So if I had used my bottom branch, how many men's names are left in my basket? 6. How many women's names are left? 3. So these are the possible outcomes, branch-wise, for 2 people going on my trip. But I need 3. So we're going to do the branches one more time. If you're having trouble sort of spacing-wise, the longer you make your branches, the more space you give yourself to write things out. If you make really short branches, good luck. You're going to be finding yourself writing really small. All right, so men and women. Oh, let me make one more comment before I start filling these in. Again, each branch adds to 1, right? So this one adds to 1. This one adds to 1. That always happens. Okay, very most top branch. I have selected 2 men to go on the trip. How many men are left in the basket? 8. Well, there's 8 people left. How many men are left in the basket? 4. So there's 8 total names. 4 of them are men. And there's 8 total names, and how many are women? The same 4 I had, right? That hasn't actually changed on that particular branch. The next branch, I actually selected a man and then a woman. Okay? That's where I am. So I still have 8 names left. How many of them are men, though? How many? 5. And so how many are women? 3. I should have put that down there. I actually had space over here. Okay. Now, this branch is actually the same branch. I mean, in the sense that I have 1 man and 1 woman. So my probabilities are going to match. I selected them in a different order, but I still have lost 1 man from the basket and lost 1 woman from the basket, or selected. So I still have the same 5 8s and 3 8s here. That's a terrible 3. I can't do that. That's better. Okay. Last branch, I've selected 2 women along that branch, right? This is my branch. So there's still 8 names in the basket, but how many of them are men? 6. And so how many are women? 2. And again, if you'll notice, each pair of branches, that did not go well, but that one, 4 and 8, 4 and 8, 5 and 3, 5 and 3, and then 6 and 2, right? They each individually add up to the number 1. Okay, so this is the work to answer the questions that come next. Feels just like when I do Venn diagrams, right? This is the work. Now I'm going to show what comes next. So here are the questions that I'm being asked according to the work that I've just done. What is the probability that all 3 selected are women? So what part of this diagram is going to answer that question? The last branch along the bottom, right? And what will I do with that branch to get the answer to my question? Yes, multiply the 3 probabilities along that branch of the 3 women being selected. So a 4 out of 10 times a 3 out of 9 times a 2 out of 8. You're totally welcome to just flat out multiply across the top, multiply across the bottom, but that sounds like too much work to me. So I can reduce, and then it'll make my process easier. 3 and 9 would be 1 and 3. 2 and 8 would be 1 and 4. 4 and 10 would be 2 and 5. At the very least, that changed a lot of the numbers to make them smaller. So even if I don't do any more simplification, I've made a lot of headway. I have 2 on the top. I have 60 on the bottom, 60 on the bottom, which is 1/30. Not real likely, right? It's not. 1 out of 30 chance that all 3 are women who are going to this particular conference or meeting or whatever. But B is an interesting question. B says, what is the probability that at least one man is selected? So what part of this diagram tells me that? What do you say, Michaela? The first branch would be all 3 men going. That certainly would be at least 1 man. Any others? Ooh, who said that? Brittany, you're right. It would be the rest of them. Every other branch has at least 1 man on it, right? Except the red one at the bottom they already picked. Now, there's 2 ways to do that. One is to multiply out all of the other 7 branches. And it will work, and then you can add them together. What's the easier way? Ariel said, I don't think so. The easier way is to remember that we had a theorem that said the probability of A plus the probability of A complement equals 1. Do you remember that theorem back in section 1? It's good stuff right there. Because what I want in this case is the probability of A, at least 1 man going. And I found the probability of A complement already on part A. It was 1 out of 30. That's the probability that no men go. And I can subtract. So what is this going to be if I subtract or I recount or whatever method you use? What is the probability of at least 1 man going? Yeah, it's 29 out of 30. Probably going to make fewer mistakes if you go that route too, because there's fewer steps. Sound good? Okay. The next example is the one that I was alluding to when I said we're going to do this one without a tree diagram, but it's going to have the same effect as doing one because I'm going to show my work in just a slightly different way. So we have a box and it contains 5 slips of paper, the numbers 4, 6, 7, 8, and 9. And a player reaches into the box and draws out 2 slips of paper, adds them together. And what we want to know is what happens if the sum is even, what the sum is, and whether the sum is odd. Okay, is everybody good so far? So what we have to do is we have to draw something that shows what happens when this guy reaches in and draws out a number from the box. Everybody with me? Okay, so one possibility is that he reaches in and he draws out a number 4. And if he drew out the number 4, what else could he have drawn out? 6, or 7, or 8, or 9. Okay, so this is the equivalent to having a branch that says 4, and then I have all the numbers, written off of it. But kind of like over here, if I draw a 4 out, I can't get another 4 because I'm not replacing the number back in, right? So these are all the ways that I could get a 4 and something else. Agreed? There's nothing else that I could do. So maybe I didn't actually draw out a 4 and I drew out a 6. Well, if I drew out a 6, I could have gotten a 6 and a 4, but I already listed that. So what else could I get? I could get a 6 and 7, or a 6 and 8, or a 6 and 9. Right? Yeah. Well, what else could I get? I could get a 7 and an 8, or a 7 and a 9, or I could get 8 and 9. So here I'm listing out my possibilities. Now, in this game, what I really care about is I really care about what happens when I add the numbers together, right? So we're going to go back and we're going to add the numbers together and see what we get. So the first one's 10. What's the second one? 11. And then 12, and then 13. So let's keep going. 13, 14, and 15. Okay. The question A asks about winning versus losing. How does a player win this game if the sum is even? So I need to go back and figure out how many evens I have. I think there's 4. How many outcomes are there? There are 10 outcomes if I count them all up. So the probability the player wins this game is actually 2/5. I mean, part B could say what's the probability they lose. It doesn't, but it could, and we could do the same thing we did in the last problem, right? 2/5 versus 3/5. The question then asks, does the probability change if the numbers are multiplied instead of being added? And if so, what does it change to? So I'm going to go back and I'm going to change my problem to do multiplication of these values instead of addition. Okay, so let's multiply. 4 times 6 is? 4 times 7? 4 times 8? 4 times 9? Okay, now let me pause real quick. You guys did that super fast, and that's really great. Is there a way that I could have just answered the question without actually multiplying those out? Yeah, anytime I'm multiplying by an even, I'm going to get an even answer. So what I could do instead of actually doing the multiplications, which is fine if you do, is I could just go back and I could find the ones that actually give me even factors. That's got an even, this one's 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 got an even, and this one's got an even. I don't actually have to multiply them. You can if you want, but you don't really have to. All of those that I highlighted have at least one even factor. How many did I highlight? 9 out of 10. Now the answer is then yes, it does change because multiplication's going to give me even numbers in a different fashion than addition's going to be giving me that. So I get 9 out of 10 instead. All right. Let's do a spinner problem. Suppose an experiment consists of spinning the first spinner, followed by the second spinner. Find the following. A is the sample space for the experiment. So I think let's do this one out in a tree diagram so you can see how it works with an example like this. And there again are other ways you could do it to show the work, but a tree diagram will work just fine. So if I spin the first spinner, I will either get a 1 or a 2. And if I spin the second spinner, after that, I will get a 1, 2, or 3. And with a tree diagram, I want to put my probabilities along my branches. So my 1, 2 branch is each 1/2. What will my 1, 2, 3 branch be? 1/3. And it's not because there's 3 numbers. Why are these 1/2s and 1/3s? Any ideas? Yes, it is. Very good. So if you look up here at the diagram with the 1, 2 in it, it's split halves, right? And while I can't necessarily verify it 100%, I'm led to believe that these are even splits here as well. Each of them is 1/3 of the diagram, okay? So that's why those are 1/3, not because there's 3 numbers, but because they're equally spaced. Okay, very good. So if we want to know what the sample space is, the sample space would be written in such a way that I incorporate all of these here into some kind of a listing. So maybe you decide, you're definitely going to curly braces, maybe you decide to just list them as a 2-digit number, like 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. You could do it that way. Maybe you decide to list them as an ordered pair. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. That would be another way to list a sample space for this. Either of those would be perfectly reasonable. So taking a look at these now, we're going to answer a couple of questions about them. 3 questions, in fact. The first of the 3 says we want the probability of spinning 2 even numbers. So, using either of the sample spaces or using your tree diagram, where do you see the probability of spinning 2 even numbers? Yeah, 2 2 is the only time that happens, right? So there's, oh, and I should actually mention one more thing. Because my diagram actually has the same multiplication factors along each branch, right? Do you see that? They're all 1/2 times 1/3. They're all equally likely. Does that make sense? That didn't happen in this crazy diagram over here, right? Those outcomes, if I multiplied along the branches, would not have given me equally likely events at the very end of each of them, okay? So that is a unique feature about this one. So when I'm comparing that I've only got 1 that I just highlighted in yellow compared to 6, I can make the comparison of 1 to 6. Whereas over here, I can't make the comparison that it's equally likely that I'm going to pick all women as it is that I'm going to pick 2 women and a man along a certain branch or even, right? Like I can't do that. But over here I can. So I actually have the probability of this as being 1 out of 6. How about spinning at least 1 2? So I've already got my 2 2 highlighted. What else would I have to highlight?
1 2 2 1 and 2 3.
Awesome. So there's 4 of them, right, Shay? Or not Shay. Samantha, your last name's Shay.
Yeah.
Okay. So yeah, so there's 4 of them that time out of the 6. And we're going to reduce our probabilities just like we would reduce any other fraction to 2/3. How about spinning exactly 1 2? I'll use my other diagram of numbers just because I keep highlighting in yellow and not unhighlighting. Which one of those outcomes has exactly 1 2 in it? Okay, so I eliminate highlighting the 2 2 because it had 2 2's in it. So there are 3 of those out of 6, which reduces to 1/2. All right, example 4. Any questions about 3 before I move on? All right, I wrote this example a really long time ago, and it's not quite the numbers that it used to be, but I still think it's probably as bad as it is. When I purchase a new shirt for my son, there's a 0.15 probability that he will stain it the first time he wears the shirt. If the shirt is stained, there's a 0.2 probability that I will not be able to adequately remove the stain. What is the probability that my son's new shirt will be permanently stained after the first time he wears it? So I put this example in because I want to show you that not all tree diagrams have equal branch structure. And this is a really good example of that. So in this case, one of 2 things happens when my son wears his shirt. Tell me about it. He either stains it or he doesn't. And if he doesn't stain it, then that branch at the bottom is done. I don't have to scrub it. But if he stains it, I have another set of branches on how I'm going to clean it, right? So either the stain comes out or it's permanent, or you can say it doesn't. But it's permanently stained. So this is a nice example of a tree diagram that's very asymmetric. So what is the probability that he stains it the first time he wears it? Yeah, 0.15, right? So this is also an example of one I've used decimals with. So what's the probability that he doesn't stain it? 0.85, and you're using the fact that those have to add up to 1, right? That's important because it didn't say that in the problem. All right, so assuming that he stains it, what's the probability that I can get the stain out? The probability that it comes out is what? 0.8, actually. I should have asked the question the other way around. The probability that's permanent is 0.2. Yeah, so it said in the problem it's a permanent stain 0.2 probability, and we have our 0.8. So this is a very asymmetric diagram. Doesn't look at all like the last one that I did. And this one wants to know then, what is the probability that my son's shirt will be permanently stained after he wears it one time? And that's the branch that it's talking about. So what would I do to find the answer to the question? You'd multiply them. 0.15 times 0.2, which gives me what? 0.03. Okay, any questions on that one? Okay. All right. This is an interesting description because I do think that there is misconception with this idea. Joe says if a family has 2 children, the only possibilities are 2 boys, 2 girls, or 1 of each. Because there are 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? Explain. So we're going to draw the tree diagram for having 2 children. So we have child number 1, and what are my options? Boys or girls? And what is the likelihood of having a boy? And the likelihood of having a girl? 1/2. And after I have baby number 1, apparently I'm going to have another. Or at least Joe's going to. Joe's wife's going to. Yeah. All right. And again, the branches will end either in a B or a G, right? Boy or girl. And what can you tell me about each one of those branches? They also have a 1/2 in them, right? So I got lots of 1/2s here. Now, the 2 branches that Joe is talking about, or the branches that Joe is talking about, are the ones that have a boy and a girl in them. So it's this branch and this branch, right? Okay. So what is the probability of each one of those branches? 1/4. Each of them are 1/2 times 1/2. Each branch is 1/4. And so if I were to add these together, that would be the probability of having 1 boy and 1 girl. And what is 1/4 plus 1/4? Yeah, it's 1/2. So why is it that there's 3 outcomes, but the outcome of having a boy-girl combination is higher than what Joe expected? Because there's 2 ways for it to happen. Yeah, there's 2 different ways for us to have a boy-girl combination. I can have a boy and a girl, or I can have a girl and a boy. So we have a lot of things we could tell Joe. One of those things that you guys have identified. So let's actually write that one down because it's a good one. Joe is incorrect. And he's incorrect because there are actually 4 outcomes, right? There's 4 outcomes. And one way to write that in a sample space, if you wanted to, is kind of like we did on the numbers just a moment ago. You can have boy, 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 girl, girl, boy, girl, girl. So you could write it like that, right? We'll write it even in a sample space notation just for fun. There's 4 outcomes. Hence, the probability of getting a boy-boy outcome is what? Because that's actually what he's trying to state for us. It's actually 1/4, not 1/3. And the issue comes from the fact that there's 2 ways of getting that boy-girl outcome. Okay, any questions on that one? Okay, great. We're going to stop there today because the next one is a long example, so we will pick back up where we left off next time.